We're going to talk a little bit about graph databases, and I'm really excited to be in New York City today, not just because New York is an incredible city, but also because it is the perfect place to talk about graph databases. In reality, though, we are all here today for one reason, and that's because of this kid. So before we get started, let's give a big thank you, round of applause, to Taylor Otwell for all the hard work that he has done and all the careers that he has helped launch. I came to programming late in life. I didn't start programming as a career until I was in my 40s. Although growing up, before working in Laravel, I did have the privilege of working with all sorts of advanced technologies. Okay, not really that last one, but literally the one before. And when I finally chose to make a career out of it, the main reason, or really two reasons, that I chose to concentrate in Laravel, and this was back in the days of version 3, was number one, Taylor, who looked at this like this at the time, seemed like a really smart and insightful guy who knew his shit, but also because the community of developers seemed to be incredibly welcoming and down to earth and helpful and inclusive. Both of these first impressions turned out, in fact, to be the case. So coming together at Laracon is something I look forward to every year. It's a chance to connect with and learn from people in person that we spend most of our time interacting with digitally throughout the course of the year. So to that end, stop by afterwards and say hi. Use this Laracon as a chance to meet new people that you may never have connected with before. And more importantly, keep being an awesome and supportive community that welcomes new developers from all walks of life and the new ideas that they bring to the table. Thank you for coming to my TED Talk. Okay. So that's me. My name's Keith Damiani. I'm the principal programmer at Titan. Titan is a web development agency. We're headquartered in Chicago. Here we are at last year's Laracon. That's me standing up in the upper left next to my buddy Matt Stauffer, who will be speaking tomorrow at the end of the day in a talk that I guarantee you will not want to miss. At Titan, we live that sweet, sweet remote work life. So we've got team members that are all over North America. I personally live in Charlottesville, Virginia. It's a wonderful place. If you're ever in the neighborhood and you're not a Nazi, please stop by and say hi. Though originally, a long time ago, I was born in Southern California. I went to college in the San Francisco Bay Area. I migrated to Charlottesville for graduate school. My wife and I have 3 children, including a son who goes to college in Houston. Sometimes, when I'm lucky, I live in Italy. Next year, I think in August, I'll be spending a couple weeks in Kaliningrad, which is over here. But currently, I'm in New York with all of you, which, as I've already said, is a fantastic place to talk about graph databases. But first, show of hands time. How many people here know what a graph database is? Don't be shy. All right, fair number of you. That's awesome. How many people have ever worked with one? Phew, okay, good. This is the part where I pretend to fine-tune my talk based on that show of hands, or that I could even see the show of hands. I could see a couple rows. But to any of the graph database pros in the audience, come talk to me afterwards at the Titan table and tell me all the things I got wrong. Seriously, I like to learn. For the rest of you, here's what I'm hoping to do today. First, we're going to talk a little bit about what a graph database is and how it works. And a quick aside here, when I say graph, I'm not talking about these things, although we are going to talk a little bit about math, just a little bit, I promise. But we're not talking about the graphs that you normally think of when you hear the word graph. We're also not talking about GraphQL, graph query language, which is, as we all know, the new hotness. Though the two can work very well together, they are very different things. So we're going to talk about what is a graph database, and we're going to talk about how a graph database differs from a relational database, what it's good at and what it isn't. We're going to go over some practical applications for graph databases, what kind of data lends itself well to the graph structure. We're going to look at some code, learn how to query a graph database, and we're going to bring it all home by talking about how this all relates to Laravel, and even more specifically, to Laracon. My goal at the end of this is to have you leave here as excited as I am about the possibilities of working with graph databases in Laravel, and hopefully with some idea of where to start. So let's get started. What exactly is a graph database? Or even more fundamentally, what is a graph? So to help answer that question, let's head back to New York City. Why do I keep saying that New York is such a great place to talk about all of this? Well, because graphs are all about understanding and working with the connections between data. And in a big city like New York, it's very easy to see, even to feel, these connections, like this in real life. They're all around you. For example, if we want to really see this in action, all you've got to do is head underground. Another shout out, by the way, to Jack McDade for the killer graphics this year. Just blew it out of the park. So, so consider the subway. The subway is a network, right? It has two key components. It's got stations, and it's got trains, which form the connections between the stations. And we can represent this network on a map. That map makes the entire system very easy to visualize, to understand, and interact with. It allows us to make decisions pretty easily about how best to get from point A to point B. Our brains can do this very quickly, very efficiently, just by looking at this visual representation of the network. The fact that a station is in some particular place is important information. But for a subway, what's even more important or more valuable is the fact that one station is connected to certain other stations. And how it's connected is also important. How far away is it? How long does it take to get from point A to point B? What subway line is it on? How many transfers are involved? At any particular time of day, what is the optimal route from A to B? So when we look at a map of a subway network, we're looking at a graph. Quick aside, if you're into subway maps, the version that I'm showing here is the 1972 version by Italian design god Massimo Vignelli. It's a modernist schematic. It's not terribly geographically accurate, but it's a masterpiece of information design. If you want to geek out about it, like I did, there are some links on my website about this and some other cool subway maps, like the London Tube, which is also an incredible map, at keithdamiani.com, which also has links to anything that I mentioned in the talk today. So a graph is very much like a map, a way of representing a set of connected data and the relationships between that data. And just like the subway has those two key components, so does a graph. It's got nodes, which in our example are the stations, and they're also called vertices in the language of graphs. And it's got relationships, or the trains, basically, or the connections between the stations, also called edges. So for certain types of data, this model of nodes and relationships, or vertices and edges, is a very natural way of thinking about the data. It's a way that we can visualize. It's a way that we would naturally draw this if we were trying to describe how data is related. If we were to draw it on a whiteboard, I would draw a bunch of circles and lines. We do this all the time. Even the word related or relationship, when we use it in real life, calls this to mind. If somebody asked me to illustrate who I'm related to, I'd draw you a family tree. Right? It's a very simple hierarchical structure. It's made up of the same basic two components, nodes and relationships, or vertices and edges. So now we have a little bit of an idea about what a graph is. A graph database, then, is a database that stores this type of highly connected or highly related data in a way that makes working with it very intuitive and very efficient, in a way that allows us to extract meaningful information out of these often very complex and convoluted relationships. But wait a minute, you say. A database that's really good at storing relationships? Don't we already have those? Aren't they called relational databases? We all use MySQL or some other SQL-based database all day, every day. And relation is right there in the name. But that's the big paradox. Despite their name, relational databases don't actually store any relationships. It fakes them. It makes them up. It builds them on every query. So consider the subway map again. This is what it looks like in a graph form. And in a graph database, both the nodes and the relationships are explicitly stored in the database. If we were to structure the same data in rows and columns and tables, this might be what it would look like. We would look at these tables and we'd say, where are the actual relationships here? Well, with a relational database, they're implicit. They're made up from connections between keys, which we manufacture under the hood using joins, or with intermediate tables like pivot tables, or in some cases with subqueries. And as developers, we've grown very accustomed to thinking and working this way. And there's a lot of power in this sort of tabular-based method of storing data, even if it's not all that intuitive. After all, relational databases have been around since the 1970s, 1974 in the case of SQL. And like many things that have been around since the 70s, myself included, they have had a long time to be optimized and improved. By comparison, graph databases are definitely the new kids on the block. Oh, I'm so glad somebody got this reference, because I couldn't leave it out. It's a much more modern way of thinking about and visualizing and interacting with our data. But even though graphs or graph databases are relatively new technology, they have their origins in a much older story going all the way back to 1735. So you recall Back at the beginning of this talk, I mentioned that I'm going to Kaliningrad next year. Kaliningrad is a small country. It's sandwiched between Poland and Lithuania. It's technically a part of Russia. Used to be part of East Prussia. And up until World War II, it was under German control, and it used to be called Königsberg. Why does this matter? Well, there was a famous logic problem back in the 1700s called the Seven Bridges of Königsberg. And the problem went like this. The city of Königsberg, illustrated here, was divided by a river over which there were 7 bridges connecting all the different land masses. I'm sorry about the nice lady down there. She's hiding a bridge. But the challenge was to decide whether it's possible to follow a path around the city that crosses each bridge exactly once and returns to the starting point. That was the problem. So along comes a Swiss guy named Leonhard Euler, who says, no sweat, I got this. Some of you may have heard of Euler. I confess, I have a bit of a math crush on him. He pops up everywhere in mathematics. He even has a number named after him. You may have heard of it. It's called E, which is Euler's number, which, like pi, is a ridiculously cool and important number. So Leo Euler pops up in 1735 and says, I got this. To solve the problem, he does what any of us really would do in the same situation. He invents an entirely new field of mathematics that we now call graph theory. He says, let's think of the city as an abstract network. The nodes are the land masses, the connections are the bridges. He figures out that no, in fact, it's not possible. And in fact, it's only possible if the number of nodes, or land masses, that have an odd number of connections to them, or bridges, is exactly 0 or exactly 2. And in Königsberg, all 4 land masses have an odd number of connections, or an odd degree, 3, 3, 3, and 5 in this case, not 0 or 2 like Euler posited. So this realization becomes the foundation of the mathematical field of graph theory. What were we just talking about? Right, we were talking about databases, we were talking about joins. So one of the things that makes graph databases so powerful is their mathematical underpinnings, the graph theory that Euler invented that powers them. It means that when you're working with highly connected data and you model the data in this way, you can get information out of the database very quickly and very efficiently to answer certain types of questions that are really cumbersome or sometimes even impossible to answer using a traditional relational database. And we've all probably experienced this. There are a lot of situations where the data that you're trying to reach is in a distant table, the data is highly normalized, and getting to it requires multiple joins or self-joins or subqueries, and the more of those joins that you include, as the degrees of separation increase and the size of your data set grows, the slower our queries become. If you imagine back to our family tree example, to answer the question, who are all my ancestors, or who are all the descendants of a particular person in my family, I either need a recursive self-join or perhaps an extra set of joins for each level deep that I want to go. And eventually, if the data set is large, we're going to reach a practical limit. Or imagine our subway map. How would we ask a relational database to traverse all the subway lines and return the most direct route from one point to another? Well, graph databases are really good at executing these types of queries, even on very large data sets. So relational databases are amazing, but they're not always the best tool for the job. And to be clear, graph databases are amazing, but they are also not always the best tool for the job. But the good news, of course, is they can coexist in a project. Laravel makes it really easy to use multiple database connections, so there's no reason that you couldn't use a graph database to answer questions that they're good at answering alongside a traditional SQL database. And we'll talk a little bit more about doing this later on. So, what are the questions that graphs can answer? What are they good for? Well, there's 2 ways to think about this. One has to do with the nature of the data itself, and the other has to do with what you're trying to get out of the data, what types of questions you want to use your data to answer. So the more highly connected your data is, or the more complex the relationships are, the more clumsy and cumbersome it becomes to squeeze that network-shaped model into tables and columns and rows. Another way to say this, another good way of saying this is, graphs are a good choice if most of the value in your data is primarily found in the relationships, rather than in the entities themselves. This is because traversing through the relationships in a complex graph that has millions of nodes can happen very quickly in a graph database. Neo4j, which is a database we'll be talking about in a few minutes, can handle 4 billion traversals per second. Janus Graph, which is a database backed by Google and IBM, can work with graphs containing hundreds of billions of vertices and nodes, terabytes worth of data, which just blows my mind. Again, this is simply because the relationships between the nodes are stored directly with those nodes, which means that the cost of finding a related node is practically no different whether your database has 10 nodes or 10 million nodes. Both operations effectively take the same amount of time. Hierarchical or tree-shaped data, like our family tree we talked about, particularly if you're querying variable depths or degrees. For example, find all the people who are related to me within 6 degrees of separation. Graphs are really good at these types of deep queries. Consider, for instance, this example of a social network. This has 1 million people, each having about 50 friends. This is a friends of friends query. So find me friends of friends a certain level deep. And as soon as you go deep into the network, they start off at about the same, the relational database and the Neo4j graph database. But as soon as you start to go deeper, the query time spikes. When we get up to 1,500 seconds, which is just under half an hour for 4 degrees, and then once you get to 5 degrees, the relationship database completely craps out, doesn't even complete the query. Many-to-many relationships in a graph database, every relationship is essentially many-to-many and is polymorphic out of the box. 2 nodes can have multiple types of relationships, and they can be connected to any number of other nodes. So if your database is loaded with pivot tables or polymorphic relationships, it might be a good candidate for a graph database. Graph databases are also schemaless. Nodes and relationships can be of any type and don't need to be defined in advance. You can put some constraints on them. You can put a unique constraint, for instance, but for the most part, you can have whatever properties you want assigned to any node, which means that graph databases might be a good choice if your tables are loaded with nullable columns, or the data model needs to be flexible and is likely to change a lot over time. So the other consideration is what types of questions are you going to ask of your data? The most common use case cited for databases is social networks, probably because it's the easiest one to conceptualize, right? But there are other cases that are use cases that might be less obvious, and one of them that I think is fascinating is real-time product recommendations. So when you think about computing the similarity between users and their purchases on the fly, often in a relational database, these similarity calculations are too slow to do in real time, particularly as the size of your database increases. So they end up requiring batch processing offline. Think about Amazon, for example, which recommends products based on the purchases of other people who are similar to me, or even predict my future behavior, or something like Spotify or Netflix. If someone has seen and liked the same 20 movies as me, it's a good bet that, and I haven't seen that movie, it's a good bet that I'm going to like it and I should be recommended it. Combinations of the two, social networks plus recommendation engines, think LinkedIn or Facebook, people you may know feature, this sort of combines the first two. Apps with strong geospatial elements, things like wayfinding, transportation networks, geographically clustered data for obvious reasons, but also related concepts like communication network, traffic analysis. Combinations of those two, for instance, a Yelp-style recommendation engine that takes geography into account. A graph is perfect for something like this. Digital asset management apps, which use similarity searches, that's kind of boring. Textual analysis and search, which is really cool, where you're looking at sort of the clustering of terms and connections between terms and looking for patterns. Even internet search, right? The PageRank algorithm that powers Google relies on graph theory. It measures incoming and outgoing connections between nodes and assigns them different values, different weights. Even the whole internet really can be thought of as a graph. This, I think, is really interesting. Financial applications use databases a lot for fraud detection. So the ability to visualize your data, it's not just an abstract benefit. There's actual tangible value in being able to look at your data and detect patterns in it. Both as a human, literally looking at your data in a graph database, but also algorithmically through things like clustering and centrality and anomaly detection. Graphs are really good for spotting these hidden patterns in your data. So in the case of financial applications and fraud detection, they sort of flip that on its head and look at the inverse. There are certain cases where patterns or clusters in your data are undesirable. Often it's an indication of suspicious financial activity, where you have transactions that are connected and are clustered, but they shouldn't be. Speaking of suspicious financial activity, graph databases are also often very useful in public policy research and journalism. There was a notable example a few years ago called the Panama Papers. It was a massive leak of 11 million documents related to offshore tax havens. Some journalists loaded these up into a Neo4j graph, and uncovered this whole web of international tax fraud by politicians and the uber rich. And you can actually access that database, that actual data, on Neo4j's website. Which is just fascinating to work with, as well as a bunch of other fun data sets that they have. They have a graph of activity by Russian trolls on Twitter in the last 4 years and how they're connected, and you can load these up in your browser and start playing with them. They're even starting to find their way into sort of the realm of big data and even machine learning and AI, again, because it's focuses so much on all these connections, which means if you start to add a graph database to your Laravel project, you can use all sorts of fancy buzzwords to sound impressive and to charge your clients more, which is really what it's all about. So these are some of the applications that graphs are really good for. What are they bad for? Well, they're not so good at a couple things, and like everything in life, there are trade-offs. So there we go. Okay. So where data is disconnected and the relationships really don't matter. In other words, if your data is primarily just a series of key value stores, or it's primarily transactional, and you're not really concerned about the relationships between the data, a graph would be a bad fit. Where most of your queries execute bulk data scans, or don't start from a known data point. Remember, graphs are really good at picking a starting point and traversing through the graph to find any number of ending points and relationships. You can index nodes by their properties, so you can find nodes quickly that way. But if you do a lot of searching of your entire graph for data that fits a general category, those queries are going to be comparatively slow to SQL. Specifying your starting node type can help, like I'm only looking for users rather than all nodes, but nevertheless, sort of a bulk data scan is going to be inefficient. Likewise, querying properties across multiple nodes can be slow. For example, if you take all the users in your database and ask the graph to find the average age across all users, that would be a very inefficient query in a graph database. Very efficient in MySQL, and that's a much better choice for a query like this. Remember, graph databases are well suited for getting the connections between data more so than they are for getting aggregate information about the nodes themselves. Also, writes to the database are comparatively slow. One of the prices you pay for storing the relationships directly in the database is slow writes, because we're effectively creating joins at the time that the data is stored. Now, in most circumstances, this is a worthwhile trade-off, right? For the benefits that we get later on the query end, but if the write speed is paramount for you, graph databases might not be a good fit. And finally, where large amounts of text or blobs need to be stored as properties. This is not true for all graph databases. There are some that are a hybrid combination of graph database and document stores, and they're fine holding large blocks of text, but Neo4j is not. All right, so that was a whole hell of a lot of theory. But in order to take advantage of all of these benefits, first you've got to get some data into a graph. So now it is time to show me the code. The most commonly used graph database, like I said, graph database platform is called Neo4j. They have an open source version that gets you really far. They also have a paid version, and they have a pretty generous program for startup companies, so it's a great choice. They also have an incredible amount of educational material, including a great O'Reilly book on graph algorithms that you can download for free. It's a really good book. A bunch of white papers. They also have, built into the platform, they have a bunch of preset or pre-built algorithms to use. Things like shortest path, or similarity, or PageRank. They're right in there, literally fire them up with a single command. There are a bunch of others. I'm not going to talk about them all because there's not time. Oh my, there's really not time. So today we're going to be focusing on Neo4j. One of the benefits to Neo4j is that it is super easy to get started. You literally go to the website, you download an installer, you boot it up, and you have your database. It's that simple. They also have a Docker container if that's your jam. Communicate with the database via an API, and results come back to you in JSON. It's simple. Requests use a particularly binary TCP protocol that's called Bolt. And then Neo4j uses its own query language that's called Cypher. And it's a pretty expressive and fun language to use. It basically takes your node diagram that we've been looking at, the node and relationship diagram, and converts it in sort of ASCII art form, right? The circles become parentheses around your nodes, and the brackets are the relationships with arrows to indicate the direction of the relationship. So you basically match on the front end whatever pattern you're interested in, and then you return it on the tail end. It's pretty much that simple. You can do all sorts of things with this. You can specify the pattern of the nodes that you're looking for, or the relationships that you're looking for. So in this case, this would find all the user nodes, named me, that's the name me, and assign it to the result me. And then we're going to use that me later on in the query to do something else. So you build up your queries with this basic pattern. So let's do some, hopefully. I have to unshare now. Cool. All right, so this is the browser. This is the Neo4j browser. I've got a little database loaded up here, and this is the interface that you use to query it. It's pretty helpful. So we're going to start off. I'm going to zoom this in because you probably can't see a darn thing. Can anybody see that okay? Okay, cool. So here's our first query we're going to write. Match, and this was kind of like the one I just showed you. Match me, user named Keith Damiani, and return me. That's it. And there I am. So it pops out the results here. This is me. I have some properties on it, which it shows down at the bottom. But that's a very simple query. Now I want to find all of my relationships. Match me, that's the same beginning query. And then the brackets, right, which is a relationship, to any other user. I'm not specifying who that user is. I just want my relationships to any user. And return me and return you, which I've proxied for the user. And here we go. Whole lot of relationships. Here I am in the middle here. You can drag it around, which is kind of fun. But you can see all these different relationships on here, right? Some of them are friends. Some of them are might like. Some of them are is friends with. There's invited. So there's all these different relationships. I just got all the relationships that I have in the graph. I can limit that now and say, OK, well, I just want my friends. So now I'm adding a constraint to the relationship. So match me, Keith Damiani. The relationship is friends with. And return it. And I'm going to limit by 25, although I don't really have to because this is a small graph. So here we are. So these are my direct friend relationships. Not many. I need some more friends, apparently. I actually don't know any of these people, but there's, 4 friends. I can switch direction. So remember our last one, we had the arrow in the relationship pointing to the right. Now we're just switching the direction, right? We're going to point it to the left, which means find the people that are friends with me in this system, right? It's sort of a weird thing in social networks that you could befriend in one direction, but in this case, it's saying find friends who are friends with me. I get back one person, Elaine, who is a friend with me. I think it's Eliane, sorry. All right, so let's make some new friends. I'm going to create a friend for one of my friends. This is Obi. I'm going to match Obi Roberts, and I'm going to match Carson Hintz, and I'm going to connect them. I'm going to create that relationship, is friends with, between user 1 and user 2. That's it. There they are. Those two are now friends. We're going to do it again. I'm going to create a friend for Carson. Carson Hintz is now going to be a friend with Lolita Heller. Sounds like an interesting person. And my command key doesn't work on this keyboard because it's a MacBook. There we go. All right. So here we go. So we just made another friendship. So now I'm going to run this query again, and I'm going to say, instead of getting my first order of friends, I want all of my distant friends. So the change here, there's only one change from the previous query, and that's that little asterisk right after is friends with. That means that's where you specify the number of hops that we're going to take, and if I don't specify a number, it's just going to keep going. So this is find me all of my distant relationships. And boom, here we go. So now, here I am in the middle. You can remember those 4 friends and then 5 friends, and now we have Obi and we have Carson and we have all these other people that I wasn't related to before because I was only looking at 1 degree. But now I'm looking at any number of degrees. And the last one we're going to run, this is a fun one. Find 6 random users who are not directly connected to me. That's a tough query to do in a SQL database, perhaps. So in this case, it's a little bit more complex. Same thing at the start, match user, where it's not me, because I don't want me to come back in the result, or, and this is the important part right here, where that user is related to me. That's all it's saying, right? So exclude those from the results. Return the results, and then grab a random set and give me the top 6. So here we go. Boom. 6 people that aren't connected to me, including test user. I don't think that's real. But either way, these are 6 people who are not connected to me. It's actually only 5 because this graph isn't that big. So, but that's a query that's very difficult to do, but trivial to do in a graph database. But what does all this have to do with Laravel? Well, here's where the rubber meets the road. Like I said, graph databases are the new kids on the block. That's especially true in the Laravel world. That's something that I want to change, and that's really my whole point in giving this talk. But I have to admit, we're in a bit of uncharted territory here. So at the moment, there's 3 primary ways to integrate graph databases into your Laravel projects. Option number 1, if you're the type that wants to sort of dip your toes into the graph pool, there's a great package called Neo-Eloquent. It's basically an ORM that allows you to interact with Neo4j as if you were using Eloquent to work with a relational database. It was created by a super smart developer named Abed Halawi. He's based out of Beirut. And it's an incredibly powerful idea. It means that there is 0 friction in moving from SQL to a graph database. You basically set up your has-many, your belong-to relationships on your model, and you're good to go. It's literally that easy. It's kind of a drop-in solution. It's great for getting up and running fast because the language and the model concepts are really familiar to Laravel developers. I do think this approach does have a couple downsides. One of them, at the moment, is practical. It only supports Laravel up to version 5.6 currently. But more importantly, it's a little bit disconnected from the conceptual model of a graph, right? And this is by design, since it continues to sort of speak the language of Eloquent and the language of relational databases. In the end, it sort of hides some of the important language constructs of graph databases that make them really powerful. Nevertheless, Neo-Eloquent is a perfect solution if you want to interact with Neo4j as easily as you do already with a relational database. Option number 2, if you're the type that likes diving right into the deep end, is the GraphAware PHP client, Neo4j PHP client. It's enterprise grade. It says it right there on the tin. You're working much closer to the metal here. It's kind of like working directly with the MySQL PDO in PHP. It basically allows you to make a connection, run raw Cypher queries, and get back results in a traversable collection. So it gives you full access to the power of Neo4j with kind of a PHP wrapper around it. So you're basically writing raw Cypher queries, which honestly is a lot of fun. Cypher is a really fun language to work with. Finally, there's a third option, one that's somewhere in the middle between the Eloquent approach and the raw Cypher approach. And option 3, actually there is really no option 3. At least there's not an option 3 yet, so stick with me here for a moment. So I built a little Laravel app using a graph database as a proof of concept, really. It runs on a Neo4j database, and it's powered by a brand new Laravel graph database driver that I'm creating, which I'm calling Laravel Vapor. I thought it was, is that taken? Crap. I'm just kidding. I'm calling it Neo for Laravel, not nearly as sexy. I should call it Laravel Vapor because it doesn't actually exist yet. So since social networks are a common use case for graph databases, I figured I would build one as a proof of concept for myself to test some different ideas on how to build a graph database driver that stays a little truer to the language of graph databases. And so while I was building this proof of concept, I found that I wanted a third option, something that's a little bit more like the Laravel Query Builder rather than Eloquent. So I used the GraphAware PHP client that we talked about as option number 2. I used that to form the connection, but then started adding a kind of fluent interface on top of it that will feel familiar, hopefully, to Laravel developers. So the app that I built to play around with, this is called Larapals. You can access it right now. I don't know how the Wi-Fi is in here, but it's at larapals.com. Larapals is the social network for Laracon, and here's the idea. So you recall at the beginning, I talked about how important this community is and how great Laracon is for connecting with other people. But let's face it, sometimes that can be really hard. Sometimes we hang with the people that we already know, and we have a tough time branching out. So this app turns the social network recommendation idea on its head. You sign up, put in your email, and start adding friends. It's going to recommend people that you should meet who are also part of the app based on how distantly connected they are from you, rather than on how close they are from you. The goal is to help you meet people that are outside of your current network of friends. And hopefully, as the conference goes on, this recommendation engine is going to grind to a halt because it's not going to be able to find distant relationships anymore. Everyone will have become so well connected and have met a bunch of people. So go play around with it, larapals.com. You basically find a friend, and chat with them directly in the app, and see how many friends you can accumulate. There's also there's a section on there in the upper right that'll show you the connections between one person and another. I call this the Wathen score, 6 degrees of Adam Wathen. You can see just how far and who is between the two of you. And also keep an eye on Neo for Laravel, which I expect to release in a few weeks. I think I'll probably open source the Larapals code at that time as well, because it's good to sort of see how it works in action. In the meantime, if you want to play with, I want you to play with Larapals, go meet some great new friends. Come talk to me afterwards if you want to talk Graph Turkey. Tweet at me at Keith Damiani, or better yet, find me on Larapals. And like I said, links to everything I mentioned in this talk are available at keithdamiani.com. Thanks so much.